Okay, so we're looking at Chapter 4, moving on to applications of derivatives. It's not as long of a chapter as Chapter 3, just the 6 sections, as opposed to last one I think had 9. But as I mentioned in class, these are going to be more thought-provoking, more word problems, less just memorizing of formulas. So let's go ahead and take a look. Okay. So first section, extreme values of functions. And first thing to do is really make sure you know what an extreme value is. So our definition is basically going to be the maxes and the mins of the functions. And when we're talking about the extreme values, it's important to remember that we're really looking at the y-coordinates of these points. So you have two types of extreme values. You have local, also known as relative, and you also have global, also known as absolute. So a local extrema is basically a min or a max, and that is basically, let's say if we're talking about the minimum, it needs to be the lowest point of any points that are around it. And the book talks about the idea of the neighborhood around it. So if you look at all the points that are close by, in order for it to be a minimum, it has to be the lowest of all the ones close by. And same idea with the max. So if it is a global or absolute extrema, and again, let's think of a minimum, then it's not good enough that it is the lowest point in a neighborhood around it. It has to actually be the lowest point on the entire graph. So a global or absolute extrema is the absolute lowest point or absolute highest point throughout the entire domain of where the function is defined. Okay. So we have an extreme value theorem, which basically guarantees us that if we're talking about a continuous function on a closed interval, that we are sure we're going to have a max and a min. Again, it has to be a closed interval, so the endpoints included in the interval. And then if we're trying to locate where that min or max would be, we check the endpoints, and then we also check anywhere that the slope is 0 or does not exist. So when we're trying to find these mins and maxes, graphically you can probably look at it and go, okay, there's one there. But if you're looking at it just with computation, you'll be checking the endpoints if there is a closed interval. You'll also be taking the derivative and setting it to 0 and solving. And then you'll also be asking yourself, is there anywhere that the derivative doesn't exist? So thinking of corners and cusps specifically. If it's a vertical tangent I put down here, if you picture what a vertical tangent looks like, it goes vertical. So your graph goes along and goes up, straight up. Well, the slope there would be not defined because it's going to infinity, but it won't give a min or a max due to a vertical tangent. So really it's just the corners and the cusp that we have to watch out for when the derivative doesn't exist. I also put here at the bottom that if the derivative is 0, that doesn't guarantee us that we're going to have an extreme value. It's just kind of the other way around. You have to make sure you check places where the derivative is 0 to see if it is a min or a max. It doesn't have to be. Okay, so for looking at our picture over here, we're given the interval that's a closed interval from A to C. So over here at A, this is definitely the highest point of any point around it. Because it's an end point and it's closed, I'm allowed to say, yes, it's higher than any of the points off to the right of it, and that's good enough to say that it is a maximum. Over here on the other end point for C, that is also higher than any of the other points off to the left of it. It's not, the function's not defined to the right of it, we don't care. So for an endpoint to be a maximum in this case, we just have to look to the one side where the function is defined and make sure it's higher than any of the points nearby, which it is. And then here at B, that would be our minimum because it is lower than any of the other points around. And again, when I'm looking at it, I have both A and C as being maximums, so we could call those local maximums, but overall A is definitely the highest of all, which makes it not just a local maximum, but also a global maximum. So your global maxes are also considered locals. Over here, B, that is the lowest point overall, so that is actually not just a local min, but a global min at B. Okay, other vocab words. So we've been talking about extreme values. I mentioned already that that's the y-coordinates that we're looking for, but we also have critical numbers, and those would be the x-coordinates. So For example, right here, b, x equals b, is the critical number, and then the extreme value would be the y-coordinate when x is b. So I don't have a scale on this particular picture, but whatever the y-coordinate down here would be is what I would call to refer to as my extreme value. So let's take a look at an actual equation here. I have this lovely rational function, and again, if I'm trying to figure out where the mins and maxes are, it's always nice to know what the picture looks like. So I went ahead and graphed it on my calculator or computer, and looking at it, I can see that there's going to be a lowest point here somewhere and a highest point up here somewhere. It looks like there's a horizontal tangent at 0. You can kind of think through that. Limit as h goes to infinity. Yes, it would give me 0. So anyway, looking at this max and this min, how exactly do I go about finding it? Well, I know that the slope of the tangent at that point is horizontal and also down here. So it's going to be, we'll need to take the derivative and set that derivative equal to 0 and find out what x values these are. And then again, the question is finding the extrema, which are the y-coordinates. So after I get the x's, don't forget to plug them back into the original function to get the y's. So here I go, derivative equals 0. I took the derivative with quotient rule up above. And when I set that equal to 0, of course, the denominator you can just multiply through by the denominator, and 0 times that denominator is still 0. So really you're just looking at the numerator being 0, and I factored out an x, and so I got either 0 or -2. And again, if I plug those back into my original function, get the y-coordinates, it comes out a half and -1/2. So I go back to my picture and kind of see if that looks reasonable. So here when x is 0, y is a half. And over here at the bottom, when x is -2, y is -1/2. So of course this from the picture, I can tell this is a max and the other one is a min. I also wanted to check anywhere that the derivative does not exist. This is a rational function. That means that there's possibly places where the denominator goes to 0, making our function undefined. So if our function is not defined, we certainly can't take the derivative of it. If you're looking at the picture, there's nowhere that shows up that's not defined, but that could just be the calculator not showing an open circle somewhere, so you have to be kind of careful. So looking at the denominator of my original function, this is not going to factor nicely. There are no, you can't factor this out. Even if you use quadratic formula, you're not going to get anywhere, any real numbers where it equals 0. So the denominator of my derivative is never going to be 0, therefore my derivative is defined everywhere. So no values coming up that I would have to check there. And for this particular function, I didn't have an interval, so there are no endpoints to look at either. So this little chart that I'm making, I like to do this for every problem. You're talking about where are your critical points. By definition, critical points are places that make the derivative 0 or where the derivative does not exist. And then endpoints are a separate category. So your endpoints are not considered critical points. They're just considered endpoints. And again, the 1/2 and -1/2 are final answers there. Those are the extreme values. So 0 and -2 are the critical points. Yeah, whoops. And a half and -1/2 are the extreme values. Okay. Another problem. I thought I would go ahead and do one where you do have an interval. So here's our function. It's a quadratic and it has a closed interval from -1 to 3. These are square brackets, so it's closed interval. So if you want to deal with that part first, we would take a look at what the function's y-coordinates are at those endpoints. So if I plug -1 in, my y-coordinate's 20. If I plug 3 in, my y-coordinate's 40. I've even drawn my picture from -1 to 3. And looking at it, up here is a height of 20, and over here on the other end, a height of 4. From the picture, I can tell that both of those values are considered maximums. Now, of course, over here, when x is -1, that's going to be my global max because it's higher than the other one at a height of 4. Okay, so I have a global max over here, and this one over here is a local max. Of course, it's a parabola, and I can see that there's going to be a lowest point where my vertex of the parabola is somewhere in between in that interval. So I would want to find out where that low point is. And of course, you could do -b/2a to figure out the x-coordinate of it, but I thought I'd stick with calculus. So here my critical values, I'm looking for where the derivative is 0 or doesn't exist. This is just a nice parabola. There isn't going to be anywhere that the derivative doesn't exist, so I don't have to worry about that. But over here, place where the derivative is 0, I take the derivative, set it to 0, I get 5/3. And sure enough, over here, that looks pretty reasonable, 5/3. And so 5/3 is my critical point. If I plug 5/3 into my function, I get a y-coordinate of -1.3, and that would be my minimum. It is the lowest point on the entire thing, which is the global minimum, not just local. Okay, I put a note here at the bottom. If it happened to have been an open interval from -1 to 3, meaning that these are parentheses, not square brackets, and the endpoints would not be included, then I would have no maximum at all, no absolute max, and also no local max, because the highest point right here would not be defined, or it's not in the interval. And so I would be getting closer and closer to it, but never able to achieve it or reach it, so therefore I wouldn't have a maximum there. And over here also, if it's an open circle, I can't call that point my maximum because that point is not on my function. Okay, so moral of the story, if you have endpoints, then you can have extreme values at closed endpoints, but if they are open endpoints, you'll never have an extreme value at an open endpoint. Okay, another example. This one, it's giving me a interesting looking equation here. I went ahead and took its derivative and I simplified it down, which maybe is somewhat of the hard part. So here's my simplified version of the derivative. If I'm looking at the denominator, I know that the denominator is only defined when the square root of something is positive. So I'm looking at what values of x can I have in here, so that I'm taking the square root of a positive number. Since it's in the denominator, I also can't have that denominator be exactly 0. So I'm really looking for 3 minus x to be strictly greater than 0, which basically is giving me this domain here with, oh, well, I put a square bracket here, but technically I can't have 3 itself because that would be dividing by 0. So I went ahead and graphed my function, and it looks like this. And if I'm looking for endpoints that I would have to check, make sure that you're keeping in mind here 3, but actually 3 is an open circle. I guess I should have made that more clear on this slide, but 3 itself gives you a 0. Oh, you know what? I take it back. I'm looking at the derivative. If you look at the original function, 3 is in the domain of the original function. I'm sorry, you guys. So 3 is in the domain of the original function. It is allowed, so it is considered an endpoint, and I do want to check it. And so I did plug it in to my equation, and I got a height of 0, which you can tell from the picture. So overall, mins and maxes, well, it's going to go up forever, so there is no global maximum because it just goes up and up. But over here, this would be the highest point in a neighborhood around it. So this is what I would call a local max. And then for the min, I would have this point over here is a min, and also this point over here is a min. They're both going to be local. They're actually the same height, so I guess you could also call them both global. Remember, the extrema is the y-coordinate, so it doesn't really matter that there's 2 with the same y-coordinate. Your extreme value would be a global minimum of 0. I put it together over here, so I took my derivative, set it equal to 0, and solved. I got my 2 values. Again, 0 and 12/5 are going to be my critical points, and then I plugged them back into my function to get the y-coordinates. And so again, if you go back, 0 and 0, you might recall, was at the origin, and here 12/5 comes out 4 point something. So 12/5, 4 point something. Let's see. Yeah, I guess that looks about right. 1, 2, 3, 4 point something, right about in there. Okay, so that was a maximum. So this one's turning out to be a local min, and this one is a local max. This one also is the lowest point overall, so we can also call it a global min. A place where the derivative does not exist, well, the denominator was this, and we solve it out again when x equals 3, which was the endpoint also coincidentally. So again, we looked at that already and said that it was a local min, also a global min. Okay, we made it through. So here's your practice problem. Go ahead and hit pause and play when you're ready. I have the solutions. Okay, so I went ahead and drew a graph of my original function y, cubic, and I went ahead and took the derivative right away also since I know I need it. And looking at it, just looking at the picture, kind of interesting right here because there is going to be a place where the derivative is 0. You know, it flattens out right there. But from the graph, you can tell if you're looking at a neighborhood around it, it's not like this point right here is going to be the lowest point in a neighborhood around it because off to the left is lower. But it's also not going to be a maximum or highest point in a neighborhood around it because off to the right is higher. So I'm expecting this point to turn up as a place where the derivative is 0, but then to draw the conclusion that it's not a min or a max because it's not the lowest point in a neighborhood around it or the highest point in a neighborhood around it. So if I go through my usual chart, here are my critical points, places where the derivative is 0 or does not exist. It's a nice just cubic, so there isn't anywhere that the derivative isn't going to exist. Where it's 0, as suspected, I was getting a value of x equals 1. So 1 is considered a critical number, but it does not result in an extreme value. So this function actually doesn't have any extreme values. There is no overall minimum or overall maximum. It goes down forever and up forever. There are no endpoints to check either. So we do have one critical number, but it did not result in an extreme value. Okay, that's it for today. I will see you guys next time.